All right, in our video chat, we were looking at part A on page 17 of our IB review problems from topic 4. And now we're going to look at part B. So in part A, they talk about it being a traveling wave that these two graphs at different times are related to. And now in part B, they sort of switch focus and start talking about standing waves. So in part B, they ask, state two differences between traveling waves and standing waves. So there's a lot of differences. Let's make sure we understand that standing waves are formed by two waves. Two traveling waves make a standing wave. One is typically going in one direction, the other is going in the other direction. They have the same wavelength and they interfere to create a standing wave. The standing wave does not transfer energy because energy is being transferred by the traveling waves that make up the standing wave, but one's going one direction, one's going the other direction, so there's no net movement of energy in a standing wave, where traveling waves do transfer energy from one place to another. Another thing to realize is that with a traveling wave, this thing moves along, and so that any particle at some point is going to go down or up by the full amount, up to the full amplitude. At some point, it'll be the crest that's at this particle, and this particle will move up that full displacement. Instead, on a standing wave, there are standing wave locations such that it doesn't move at all, and there's others where it moves a lot. So where you are determines how much you end up moving. Where on a traveling wave, any particle eventually ends up moving the whole amount as the traveling wave eventually goes by there, versus on a standing wave, some particles hardly move at all and others move a lot. They have different displacements, and thus they have different amplitudes. You could also talk about how this particle has a constant amplitude, it's never changing, where this one has a varying distance that it'll move depending on where the traveling wave is coming by. Last thing they talk about in the mark scheme is something between phases, and notice that all of these particles, all of them, move up at the same time, and then they all move down at the same time. Where here, some particles are moving up, while other particles are moving down. So here you'd say all the particles are in phase, or 180 out of phase if you have one of these. Then these are going up when these are going down, but they're all either in phase or 180 degrees out of phase. With a standing wave, we're on a traveling wave, every single particle is doing its own phase as it goes by, and only particles that happen to be an exact wavelength apart will be at the same phase. And that's the major differences between a standing wave and a traveling wave. And they only wanted two of those marks. Look at the mark scheme and see what you would do there. Okay, let's look on. Part C, explain what is meant by wave speed when you're talking about a traveling wave. So that's typically most often thought by the wavelength divided by the period, or the velocity at which energy is transported, because a traveling wave is transporting the energy. So the transfer of energy rate in meters per second. But make sure you mention energy, and this equation helps you calculate it, but it doesn't define it. So don't use the equation for the definition. For the definition, you want to talk about the rate of energy transfer, how quickly the energy is moving. For standing waves, it's a little trickier. So you have to actually talk about the component waves. So it would be the speed of the component waves, one going one way, one going the other way. Those underlying component waves determine the speed of a standing wave. So it's actually referring to the underlying waves in that case. So here's a first harmonic, closed, closed. This is first harmonic, closed, closed. And they're showing it at one point in time, and then they're showing it half of a period later as this string goes up and down and up and down and up and down. I think we saw that in class enough times. And part one asks for explain how the standing wave creates a sound wave. So, and you go, what? This is confusing. So I read the question again more carefully, and this is a string that's vibrating. This is like a guitar string going up and down, and it's going to be going up and down, the string is. But that's not the sound. Okay, don't confuse this with a pipe that's closed at both ends and there's a sound wave inside the pipe. That's not what this is. This is a string. So how could a string that's going up and down make a sound wave? And you got to stop and think for a minute. There's 2 marks, so it's kind of complicated, I guess. So let's think about sound is the movement of the particles vibrating longitudinally. So if I think of some air molecules here, and the string comes up and sort of pushes them and then pulls away from them, that can create these pressure changes that is creating the movement of the sound. So the string moving is what's pushing the air, which is creating the sound waves. So my light in my classroom just went out, but I think you can still see decently here. Maybe I should mount a light. That's a good idea for my next one. I'll see if that helps. Anyway, I'm going to keep going here. This is not the speed of the wave in the string that they talk about in this next part. This is the speed of the sound that with the string made that then is going off into space. So the speed of that sound is what we're going to talk about, is 340 meters per second. And the length of the string is 0.8 meters, and the speed of the wave in the string is 0.8. So if we talk about the string is one thing, if we talk about the sound, that's another thing, and they've mixed them all together here to confuse you. So don't let them do that to you. Instead, you want to make sure they keep them separate. So the one that we know the most about is the string, and for the string, we know that the wavelength here has to be twice that. So the wavelength is going to be 1.6 meters. And we have the speed, so we can say velocity is frequency times wavelength. So wavelength would be the velocity divided by the frequency. And they're asking us to calculate the wavelength of the sound in the air. So I guess we have to use frequency for that. So what I would do first, this 3 marks is like, okay, wait a minute, there's some work to be done here. So if we're going to be getting the wavelength of the sound in the air, we clearly know the velocity in the air is 340. And now we wish we knew the frequency. But the frequency that the sound is being made is going to be the same as the frequency of the string. So I can go back to the string at this point and try to think about for the string what's going on. And for the string, we have the wavelength of 1.4 meters, but we also have the velocity of the string, which they gave us is 240 meters per second. So for the string, we have velocity. So for the string, we have velocity is equal to frequency times wavelength. And so the frequency is equal to the velocity divided by the wavelength. So we get the 240 divided by the wavelength, which was 1.6. So we get 150 hertz for the string. And now we're going to use that frequency over here for the wavelength of the sound. And so we get 150 in here. And so that ends up getting us our 340 divided by 150 gets us our 2.3 meters that we get for the wavelength of the sound. And that's the end of that question. So there you go. I hope that helped. Sorry this is so blurry. I think I'll try to work on getting a better light, but hopefully that helped you to do this last problem on the IB packet.